Greetings all. So we've just seen how to do the vector operation called the dot product, which is a really simple calculation but doesn't appear to make anything in and of itself. And as I indicated, think of the dot product as a power source or a key component of other more significant measurements. You need it, the dot product, to go build other items. So the first of those items is the angle between two vectors, and I'll have another short follow-up to this segment. It comes later. And let's just look at two vectors. Now remember the two aspects of a vector. Probably should do this because we're still so new in the course. We should be seeing direction and magnitude, but location is not one of those two aspects you have to have. So this formula sort of goes along an assumption. If the vectors originated from the same point, what then could we determine about the angle that is between the two vectors? What could we determine about the angle that's between the two vectors? So in this video, I'm just going to use the formula as if it's something you already have. A lot of our trigonometry professors actually derive this formula for 2 dimensions in their trig classes, and the pre-calculus teachers endeavor to utilize it, maybe even in 3 dimensions. I have the derivation as a separate video segment. You really should go through this. Math, engineering, computer science people, they need to know that things are going to work. They need to be able to verify. And sometimes you can't build it from scratch because it's that advanced, but you have to use it. But part of the growing process is to improve that skill. So here's the formula. The cosine of the angle that's between the two is the dot product of the two vectors divided by their two magnitudes. There's other ways of stating it aloud. And again, I'm going to go through the derivation in a separate video. It uses the law of cosines from trigonometry. We're just going to use it. So here is our first example. Two vectors, 3, 5, and 6, -1. Those are our two vectors, two-dimensional. They even kind of look like these two vectors. Goes right and up, and this one goes right and down a little bit, just like these two do. So the cosine of the angle, not the angle, but the cosine of the angle, is equivalent to the dot product. 3 times 6 is 18. 5 times -1 is -5. Find the sum, which in this case is subtraction. So the numerator is 13. Divided by their product of their magnitudes. 3 squared is 9. 5 squared is 25. That's the square root of 34. 6 squared is 36. -1 squared is 1. That's the square root of 37. Now, in my course, in my syllabus, I discussed that we generally won't use technology on our exams. We'll use them for other applications. Leave it like this. If you don't have access to a technology right in front of you, if you were to go to your calculator, then you'd have to determine degrees versus radians. How does the instructor want it? Usually it has to do with the application, whether you need degrees or radians. For this particular problem, it generates a value where theta is approximately 68.5 degrees. And look, even the picture, it's just about believable that it's about 68.5 degrees. So theta we can't find without technology. But there is something we can determine about theta. And that is this little piece of information. If the cosine of theta is a positive value, what that means is if cosine of theta is positive, or cosine of theta, more appropriately, is greater than 0. Well, that happens if I use a circle representation. That only happens in quadrant 1 or in quadrant 4. I will, before I'm done, explain why quadrant 1 is the only answer we're going to look at when we're measuring this angle. But other applications may ask you to know the quadrant 4 result. The vectors are rotated, so you really can't know what quadrant you're talking about anyway. If I rotate this picture sufficiently, you wouldn't know what quadrant you're in anymore. So we'll take the one that the calculator gives us for the moment, 68.5 degrees. Let's do another test of this. Oh, what do we call that when the angle's in quadrant 1? What did my geometry teacher call that? I think the term was that theta is acute because we know that we got a quadrant 1 result. I'm going to say it, here's my reason, because cosine of theta is positive. Acute, that was the term from geometry when it was less than 90 degrees. All right, next example. Scroll back down, here we go. Cosine of theta is the dot product of the two vectors divided by their two magnitudes. In this particular case, 2 times 3 is 6. Negative 1 times 6 is negative 6. 4 times negative 2 is negative 8. Divided by two separate magnitudes, it's going to be negative 8 over some quantity. Now let me pause here and let me rearrange the information I gave to you from the previous example. I will need a calculator if I want to approximate theta. If I want the exact value of cosine of theta is exactly negative 8 over, I can leave it like that for the exact solution. I am interested in knowing what theta is approximately equal to out of curiosity, especially if I'm an architect or engineering something. But because the cosine is negative in the second and the third quadrant of our trigonometry measuring tools. So I can already tell you that theta is, oh no, what's the word when the angle is larger than 90 degrees? What was that term again? Oh yes, obtuse. I already know theta is going to be obtuse because cosine of theta is equal to a negative value. This is not very nice math notation, but it's like a shorthand that I would accept under desperate circumstances. Now let's go back to the calculation. What if this truly was the question? Find the cosine of the theta. Who cares if it's messy? Find it for me. What would you type in your calculator? So what's the magnitude here? 16 and 1 and 4. That's the square root of 21. 936 is 45 and 4 is 49. Yes, I do know that that is equal to 7. But I don't know this exactly, nor does that square root reduce. I'm just going to leave it like this since I'm not forcing the technology on you. If we were going to be in an algebra class, oh, we would rationalize the denominator and have all kinds of fun with it. All right, one last little detail about angle between two vectors. Let's suppose that the first vector was aiming in this direction and the second direction was aiming in this direction. You can't really talk about quadrants for the angle between them because neither vector starts in the x-axis direction. So the rule of thumb is you choose the shorter or smaller angle to call your theta. You'll never see a theta that's more than 180 degrees, like this. You'll never see that one being measured. We'll always measure this one. So when we use the cosine of theta formula, we only get values that are between 0 and 180 degrees, or from 0 to pi radians. All right? I'll show you something else in the next segment that's a rather significant feature of the angle between vectors.